Welcome everybody, this is Mr. Cloud coming from his home in North Belmore. This is March 2020 and I'm going to break down a free response question with you on air pollution. Let's get right down to it. This is something that we will see potentially on the AP exam. This is a common set of questions that we'll see for chapter 15 in the Friedland book. And this is one of the part 2 questions I would actually give in class. So we're going to break this down together and talk about what you get credit on, what you wouldn't get credit on, and kind of give some test hints too. Okay, so let's read through this together. First things first, direction says answer the following question, blah, blah, blah. You know this already. It's about 22 minutes per question. Questions range between 10 to 12 points like that. It says that the 6 criteria pollutants used by the Environmental Protection Agency to assess air quality in the United States are NOx, SO2, carbon monoxide, lead, ozone, and particulates. And that NOx is nitrogen dioxide. The graph below shows trends in the concentrations of 4 of these in a certain city in the United States. So let's scroll down a little bit more. So what do they give us here? They give us atmospheric concentrations of ozone and carbon monoxide. And we're going to look at the trends. First things first, whenever you get graphs on the AP exam, you're going to break down the trends, take a look at what's going on, and then go to the question. So right here, I have ozone and carbon monoxide, and it looks like the carbon monoxide is going down pretty steadily from 1976 through 1995. Ozone, if you put a line of best fit here, it looks like it's going down, but it's kind of more stationary. Then we go down to lead and particulate matter. Particulates, I guess, were not really measured at this particular city until the late 1980s. And lead levels have gone down precipitously. They're at about 1.5 or so in 1977, 1978, and has dropped off a whole lot ever since. Most likely that's because of the Clean Air Act that was passed in the early 1970s that made leaded gasoline illegal. We'll talk more about that in a little bit. Okay, so let's get into it. The first question says, calculate the percentage change for ozone and lead in the atmosphere from 1978 to 1988. So we have a 10-year frame there. It says identify and explain. Those are the 2 main things there. Identify and explain the trends uncovered for both ozone and lead during this 10-year span. Well, first things first, let's break down how to calculate this. Now, in the AP exam, there are going to be certain calculations you need to know. One of them is going to be rate of change. This is going to be a percentage question. What are the other things you need to know? One, dimensional analysis. Another, doubling time, growth rate, are all of the main parts of math. In 2020, it's the first year you can use a calculator on the exam. So a lot of students are pretty pumped about that, but hopefully that doesn't mean the math is going to get harder. We'll see how that goes. So first things first, let's do that. We're going to go and check out the first question. So here we have, guys, the first question here, percentage change. So in this case, I'm doing an example for lead for you. So I have percentage equals initial minus final over initial times 100. Standard percentage change, right? So going back to the chart itself, guys, if I make my way up this way, I look first at ozone. We can do that first. We're doing lead. We're going to go to lead. 1978, we're at about right in between 1.4 and 1.6, so I'm saying 1.5. And then in 1988, making my way this way, ballpark it. I have 0 at 0.2, 1988 right in between. Let's go 0.1. That makes sense to me. And again, if you're in the ballpark, there's going to be a range of an answer that you can give to get full credit here. So if you came up with, let's say 90%, as your final here, you'd be fine. So 1.5, which is your initial concentration of lead in 1978, minus 0.1, which is your final concentration of lead in the atmosphere at this particular city. Units are, I'm not dealing with units right now, but it's important to write those. But in this case, your final answer would be fine. Over 1.5 times 100, that's going to be give me 0.93 times 100. I'm moving the decimal place over 2 places at 93%. So man, it dropped off a lot in a 10-year span. Okay, so let's go back to the question. All right. And you do the same for ozone, and your final answer should be around 13%. Whereas it lead at 93. The next part says, Identify and explain the trends uncovered for both ozone and lead during this 10-year span. So identify the trends. So we're going to talk about the numbers here. Give us the data. What has happened in the 10-year span? Then explain why that trend is happening. Keep that in mind. So you're identifying the trend and then explaining the trend. That's important here. Okay. So identify. Both ozone and lead declined from 1978 to 1988. The percentage of ozone fell by 13%, whereas lead fell by 93%. Good for you. You just got points there. Most likely that'll be a 1-point response. Explanation. All right, so what I did is I actually went through this together and answered fully the way I would actually be doing it. So lead fell much more than ozone. The vast majority of lead in the atmosphere came from mobile sources of air pollution, specifically the combustion of leaded gasoline. The Clean Air Act banned the use of leaded gasoline in the United States, which proved very successful. Ozone levels remained consistent over the 10-year span due to the fact that the sheer number of vehicles on the road increased, which continued to contribute to photochemical smog in densely populated regions. Now, do I expect you to word everything the exact same way as I would? No. But what's important here is that I'm explaining why there's such a stark difference here. Yeah, we get it. They both dropped off, but why the heck did lead drop off so much more? And it's because of legislation. It's because of the Clean Air Act. Okay, so that would be a full. That's a 5. That's a 5 response. Is what this would be. All right, moving on. All right, guys, let's move to the next one. This is part B. For either particulates or carbon monoxide, identify the major source or sources of the pollutant, and describe the most effective method of reducing the concentration of the pollutant in the atmosphere. So what I did here is I broke down one of them for you. So we talked about particulates. And what are particulates? Particulates pretty much is anything floating in the air from a particular source. So what are those sources? So that would be the first part, identify sources. So what I have here, particulate matter can derive from numerous sources, such as the combustion of coal or combustion in general, unpaved roads, forest fires, any way that particulates get up into the air, you'd have to list, and you would get credit for that. Okay, so if you have any one of those and not limited to those, you would be fine. Okay, describe. All right, so it also says, describe the most effective method of reducing the concentration of the pollutant. So if you were working with particulates in this particular circumstance, you could talk about some technology like wet scrubbers that could remove the particulates before they actually leave the smokestack. So specifically a wet scrubber, what that does is it sprays water and then some sort of base, which is usually lime, that neutralizes what's ever in there, and which will remove the sulfur dioxide gases. But the particulate matter just kind of gets caught up in the water there and pretty much falls straight down where we collect it. It becomes a sludge. We'll collect it, we'll put it on trucks, and we'll actually bring it to a landfill and we'll bury it. That's one way to limit the particulates coming out of a smokestack. You can also use electrostatic precipitators. With that, guys, you have a difference in charge that's happening there. There's an electrode that goes straight up on this precipitator that provides a negative charge, attracts to a positive charge on the wall, and then it kind of drops off as dust, and we collect that and landfill that too. So that would be a full response for this question, guys. Carbon monoxide, on the other hand, that's an incomplete burning of a fossil fuel. You get carbon monoxide. That can happen if you have, let's say, lumber being burned in your home for heat. You can get carbon monoxide if the actual chimney is not vented properly. Space heaters using fossil fuels could cause that too. So you have to avoid that and have proper ventilation to remove carbon monoxide. Carbon monoxide also comes from vehicular exhaust. So you never want to run a car, guys, in an area that's confined. Ventilation is key for carbon monoxide to be ventilated out. Okay. I provided a link here, guys, to the EPA, which will give you some more information about particulate matter, especially the particulate matter 2.5, which is the worst type of particulate matter, which could really cause lung issues if inhaled dramatically deep down into your lungs. Okay, moving on to the next one. I hope this is helpful for you guys. All right, moving on to the next one. Here we go. Here we go. Bang. All righty. In recent years, results from scientific studies have increased public awareness of the possible damage to human health from exposure to indoor air pollution. Identify one specific indoor air pollutant, and for each, discuss the following. Okay? You're going to discuss all these things. One, source of the pollutant, where it comes from. Source always means where it comes from. The pollutant's effect on human health. How does it affect us if we breathe it in, most likely, or exposed to it? And the method of prevention or cleanup of the pollutant. So this is indoor air pollution specifically. Moving myself around here. Okay? So common responses. You can have carbon monoxide, super bad, not good. Cigarette smoke, radon, which comes from radioactive decay within the bedrock surrounding your home. Formaldehyde, which is an organic toxin that can be found usually in upholstery, or carpeting or something like that. So an example of one would be cigarette smoke. Well, what's the source of cigarette smoke? It could be secondhand smoke. It's just tobacco, cigars, cigarettes, whatever it might be inside the house. Human health, it's a carcinogen. We all know that. This is a home run question. This is common sense here. It's a carcinogen. Chronic exposure to secondhand smoke can lead to lung cancer. You're good to go. 3, the method of prevention or cleanup. Well, prevent anyone from smoking indoors. Don't smoke in general. Moving on, right? Radon. All right. I think this is a quality answer when you're talking about radon. Radon, again, happens because of radioactive decay within granitic bedrock. Some areas have more radon than others. Long Island, where our bedrock, is pretty young, so you don't see radon at high levels. Usually residual bedrock that's been there for a long time within the continent, more like inland, has a higher concentration of radon. So that's your source. If chronic exposure exists, radon can cause cancer, especially worse for individuals with underlying health effects. So if you smoke tobacco, if you're a tobacco smoker and you're exposed to radon, your likelihood of getting cancer is much higher than someone else. Okay? And how to prevent it? Make sure all cracks in the foundation of a home are filled. Keep house well ventilated, consistently opening windows, and you should be fine from that exposure. Okay, so those are 2 examples. You could have said asbestos, house cleaning products as well. You could have had that in your answer too. So like some organic chemicals that could be left in your house, like that. All right, moving on, guys. All right, guys, to the last question here. Okay, let me move this down a little bit onto a full page here. All right, guys, chlorofluorocarbons, right? CFCs, something that we would have talked a lot about in class if we were together. As we know, guys, chlorofluorocarbons go right up to the stratosphere. Sunlight comes in, it breaks them apart, and oh no, we have some chlorine in there, man. No good. All right, that's going to act as a catalyst to break apart ozone. So what we're going to do, guys, is explain the process by which CFCs lead to the destruction of stratospheric ozone. And you know what, guys? This is right from sample AP exam. And you know what I'm going to do? I'm going to try to pull that up for you right now. All right. All right, guys, I'm back. Sorry about that. Had a little technical difficulty there. Could not find where the 2013 free response was. So I get inspired by actually just looking at old AP exams, and some of the questions that my students actually answer all year are from old AP exams. So this is the actual question from the 2013 test. It says the Montreal Protocol in 1987 provided a global framework to phase out chlorofluorocarbons. So it sounds exactly like the free response you just had. And question 1 says explain the process by which CFCs lead to the destruction of stratospheric ozone. So how do you answer this? Well, what it boils down to is you have to talk about specifically how really CFCs go ahead and do that. So first things first is you could say this. Absorption of UV radiation by CFC molecules releases chlorine atoms, right? And then you're just writing it out. So this is actually acceptable. The absorption of UV radiation, so here's your CFC. UV comes in, so here's my CFC over here. UV comes in, bang, breaks it apart, releases chlorine, right? That's the main catalyst that's going to break down ozone. Then you still have the next step, guys, right? And the next step is going to be then chlorine atoms break down ozone. You full credit. That's what you would need. Okay, so a 2-point type question that you would have there. So once again, UV breaks down CFC to release chlorine. Chlorine breaks down ozone. Done. You could do it using formulas as well. If you know it, you can do it. Okay, you can do that as well. All right, the next part of the question. Okay, it says number 2. Explain why tropospheric ozone is considered a pollutant, whereas stratospheric ozone is not. So first things first, this is always really confusing to APE students. All right, ozone itself, O3. So one flip of the coin is that ozone is what we rely on as a biosphere to keep us protected from UV radiation. But where does that lie? That lies in the stratosphere. So stratospheric ozone is a requirement for life. Without the ozone layer, guys, forget it. All right, we wouldn't have life on Earth. Net primary productivity would completely drop out. Ozone protects, all right, us from that. But where is that? Stratospheric ozone. So that's not considered to be a pollutant, okay? Whereas tropospheric ozone is something that accumulates because of photochemical smog, right? And it's really a product of that. So that's your main difference. So a sample response would be, tropospheric ozone is a product of photochemical smog and can be considered a respiratory irritant, whereas stratospheric ozone occurs naturally within the stratosphere and is essential in the absorbing harmful UV radiation that could reduce biodiversity if not gone unchecked. So that would be an example of a response there. All right. So pretty much, guys, that is a wrap. I hope this video was helpful to you. Let me know. I'm going to upload it on my YouTube page and link it over to Google Classroom. Thanks a lot, guys. Have a great night. Hope to see you soon.